So, okay, I'm Sid. I won't introduce myself and bore you. So let me introduce Akarsh. Akarsh Verma is a consultant with 9 years of experience in designing IT capabilities using tech and data. He has worked as an enterprise architect for verticals such as automotive, manufacturing, NBFC, and FMCG. He's an active speaker and contributor in communities related to software architecture and machine learning. Now his session will be kind of a dialogue uh, towards taking an ML experiment and turning it into a reliable software system or an MVP if you will. So the session is going to be a little long drawn, and there will be question breaks in between. So please feel free to post your questions as you hear the talk. Thank you. Akash, over to you.
All right, Sid. Thank you. Thank you. I really like the way you have called this a dialogue.
Yeah, absolutely. Over to you,
So,
sir.
Archit, can I share my screen? Mister?
Uh,
Yes.
All right.
Not yet, Akarsh.
Okay.
Can you share it again, please?
Yeah, sure. All right. Let me know if that's visible.
Yes, it's live now.
All right, great. Hi, good morning, everyone. I'm Akarsh Verma. Nishchay, can you also give me a cue if I'm visible to the camera?
Yes, yes, yes. All good.
All right, great. Hi, good morning, everyone. I'm Akash Verma. We'll be talking about architecting a scalable machine learning pipeline. As Sid mentioned, this will be a dialogue, and we'll just see through how to take a problem, how to take a business problem, and how to work with different set of peoples in the team, data scientists who are working with building models, and how to effectively take that business problems and those models and productionize them, as I like to call them. So this is just going to be a 2 hour talk, and we'll have question breaks in between. So let's get started. So a quick introduction about myself, and that's me and my marketing picture. You have already seen me how I really look. So I'm an analytics consultant at Thoucentric, and I'm an enterprise architect by profession. I practice cloud and specifically focused on analytics and emerging technologies. And this is the slide which I would like to start our journey around. Now, if you see the caption, imagine what is happening behind the scenes. There's a Microsoft says, or PowerPoint effectively told me, and the description was auto-generated really, is that a person wearing glasses and smiling at the camera. Now, it's able to tell that there's a person, one, it's able to tell that I'm wearing glasses and I'm also smiling, which is kind of great. So the things that could have happened in the background could be that Microsoft would have looked at this image. They would have probably sent it to a server or have some model manually downloaded, coupled with PowerPoint installation. And then the model would have probably inferred it and done some generative network to come up with the text that it is doing. And the description is subtly accurate. Even though it does not know me, the picture is almost perfect. This is as good as any other human being could be by just looking at this image. Now, imagine the number of PowerPoint users happening in the world, and imagine the scale at which this is being done. This is one of the most simplest examples of ML at scale. And this is how we could know that AI exists in the world and is deeply integrated into our lives, into our business operations. Even when we are using Teams, there was this nifty little feature which is now blurring the background and now superlaying it with beaches and whatnot. So these close integrations of AI is what makes our world easy, and also what challenges us to design and build systems at scale. Now, with that thought, let's move on to something where our talk is focused around, which is data. We have looked.
Akash, sorry to interrupt you in between. I think we lost your video feed. Can you check if your webcam is on?
I've switched it off right now for smoother audio. Hello.
Yes, Akash. Your video is not coming. Your webcam feed.
Let me check that. Is it back now?
Yes, it's visible,
Oh,
and We are live now. Thank you.
All right. Sorry for that. So while I started talking about data, you must have thought a little bit on the what are the different data sources available in the market. And each of us work with data. Data is effectively the salt in all our systems, in all our business operations, be it retail, be it e-commerce, be it finance, where we get a lot of structured data. The data is tabular. You can really put it in an Excel sheet. You can really kind of put plots around it, have rows and columns, do calculations on it, do functions, lookups. VLOOKUP is very popular, and whatnot. But on the other hand, there are social media information. There's data coming from unstructured sources. It could be Twitter, Facebook, or just your app ratings, or your Play Store reviews, or your Zomato reviews if you're a restaurant owner. And all of these data sources are equally important as the structured data sources. Effectively, they give us an insight, they give us a trend, they let us know that how my customer is thinking and what is good or what is bad. And while we have ratings in most of the places, the numbers themselves don't imply or don't provide any insight. So there's a need to look at structured and unstructured data as well. And all of that combined together is usually what gives a lot more insights than just the traditional way of MIS systems. With that thought, this data, this has grown significantly, and it flows through various different sources. It could be internal systems, it could be news articles, economic indicators, sales figures, marketing information, and then we have now IoT, which is becoming so popular, where we are getting data at such large speed that it is very difficult to process it. We have a different, and we need to come up with a different design to specifically adhere to those kind of needs. And then the challenge is that growing business demands are also warranting that the entire gamut of this data is looked, and everybody is data hungry. The problems that we try to solve is customer segmentation, customer churn, demand forecasting, which was just a previous talk, marketing insights, and whatnot. But with that, the core fundamental problem still lies that data is growing and is growing at a significant rate. I think that I was reading some statistics, and there's probably terabytes of data that is being generated every single day. And the rate at which this in this growth is also increasing is also of paramount importance. So moving on a little bit. So we have talked about data, and we have talked about how it is growing and what are the different sources from which we get data. Loosely, what are the different kinds of data, structured, unstructured. But effectively, unless we are an R&D paradigm, unless we are doing and playing and tinkering with technologies, building technology-based products, most often than less, we are trying to achieve some business value. We are trying to solve a business problem where we need to do some sort of an imagination as to what my customer wants and what could be the report that could help me achieve more business value. We always want to come up with summary numbers, and the need for this grows as we go higher up in the ladder in the organization. So typically, when we are looking at operational structures in an organization, they would typically be the one who will be generating the data. And the systems are not important really at this point. It is just that where the data is generated, the source of data generation. And then slowly up the ladder in more strategic verticals of the company, people would imagine what to do with the data. For example, if you are into finance, you would worry about how my collections could be improved so that my debt is reduced. If we are into some sort of a demand forecasting, we'll have sales people, we'll have marketing people, but effectively we'll try and at a strategic level, we'll try and see how we could even improve that demand or the demand forecasting accuracy by a couple of percentages. And that's a good enough number to warrant the need for analytics and to warrant the need for such systems and effectively look at all this data. And then when we have imagined those problems, when we have thought about what we need to do, what are the reports that we need to come up with, we effectively come up with a problem when we need to integrate. It was really easy when we started with the Excel sheet and when we were just doing formula operations within the Excel sheet. However, the moment we start thinking of systems, we effectively need to integrate with all the different data sources, be it internal or external or purchased or structured or semi-structured. And that's when we go to IT, which is a department which is usually isolated in the company and which is where the cool hats stay. Now, IT typically would help us to design and envision such a system that could enable that reporting, which in turn impact the business value. Now, what IT would help achieve is they'll help us develop, deploy, and monitor such a system which effectively, over a period of times, realizes that business value in an incremental way. There might be an upfront cost to it. There might be an upfront cost to building the digital resource or the asset that we are trying to strive for, or the analytics report or the machine learning model. But effectively, that's what IT helps us achieve. It is develop, deploy, and monitor. And then there are more phases depending. This is a generic way of laying it out. And all in all, I like to think of this as a way or lose integrations or touch with architecture. So architecture really is a discipline that is spanning across, and it also helps business imagine things in a more structured way, kind of a framework which allows business to think and plan out their IT implementations. There are other aspects of enterprise architecture as well. And then the next four steps after imagination is where architecture has some roles to play depending on the level of depth it goes on to the implementation. So now we could be talking skills, we could be talking development strategy, we could be talking uh, frameworks, technologies, and also monitoring ways to envision the business value. So architecture whole and whole kind of impacts the overall software development lifecycle and is important to play. It's an important role and a need and a capability in the company. Moving on, I touched upon the data is salt of software applications, and even though we are building large-scale enterprise systems, we cannot eliminate the need for a good design, because effectively what would happen if we do not target a good design or a scalable design is we would fail. And that has happened a lot of times with a lot of companies. They designed a system which is not adaptable, not scalable, not cohesive, not really easy to integrate. And all those quality attributes are something that we'll talk about in the upcoming slides. Now, in order to do that, before we jump on to the technicals and the jargons and the details around architecture and non-functional requirements, I would like to start with a simple example and create a fictitious company. So it was just a bang on product. So me and my friend, we thought of creating hoodies, and instead of going to Goa, we just started designing a t-shirt or a hoodie that needed no washing or cleaning. And the idea was super simple, but it very, very quickly spread like wildfire. And the reason for that is the product is picture perfect. This is what I would like to think as most of us as business owners effectively do. We think our ideas or our products are effectively going to change the market. It's going to revolutionize it. And that's what we thought on the pixelhoodie.com. It needed no washing or cleaning, and every student of every type of every college wanted it. So the problem was simple. We were manufacturing t-shirts, and initially we gave the manufacturing to some local tailor, and that's it. We were doing the marketing and distribution all by ourselves, and the life was easy. We made a ton of profit. And this was where we had good reception, we had a good response from the market, a good feedback, and then somebody told us to scale our business operations. That's when we effectively thought of going online. This is a time effectively as our sales was soaring. We went online, we went different e-commerce platforms, we kind of talked to different providers, we integrated with different e-commerce platforms. Some of them were selling things digitally, and then there were some manual operators who were ready to do a distribution channel for us. They're kind of our own distribution partners to different cities. Now, as we grew, we had a lot of different challenges. We wanted to know more about our business and how we were doing. When we were good or when we were performing or operating at a college level, we were effectively able to manage and maintain everything in an Excel sheet. But now we had too many data sources and formats because each e-commerce provider had their own data format. One of them said JSON and somebody said a CSV, and then there was a pipe delimitation, and then somebody wanted an API and whatnot. Finding insights by looking at the data was becoming more challenging because of the too many different data formats, sources, and also the magnitude of the data itself was growing. The frequency at which we got data was different, and hence it was very difficult to find the total sales that we were effectively doing and then kind of do a drill down analytics on it. We wanted to find out college-wise sales. We wanted to see how we are doing in distribution of years, like first year students are buying more t-shirts or final year students are more. What is the gender penetration? Are girls more buying it or guys are more adapting to our t-shirts, and all of those different insights. And a lot of those insights, as we later find out, were not even visible to us. We were not even looking in the right place. We were looking at the right problems, but we were not looking at the right place. And that's all because of the growing data and the growing different integration sources. Now, that's when we had a consultant, and he told us a lot of different stuff. We had a workshop about 2 weeks that was extremely nice. And we talked about machine learning, we touched on statistics, we touched on cloud, data science, data engineering, dashboards, graph, services, virtual machines. And after the end of 2 weeks, it was all Jupiter and moons to us. We had no clue. We really had no insight as to what we needed to do because all we were a couple of college kids who really wanted to sell t-shirts. And we had no understanding of these things, all of these key terms and how they played with us, how to go about it. So that let us again back high and dry. And then we went back and we did a little thought exercise and we studied as students we were used to. Now that's when we realized there are certain frameworks in the industry that allow us to perform and understand the problems that we needed to. So these frameworks were very generic, and these frameworks were not really tailored for an industry or for a specific problem or for a specific kind of report or had any good jargons in it. They were pure simple English. And what was happening was that it was very easy and intuitive to us. So we ran towards those frameworks. It was really nice, and we were switching on to that. One of those such frameworks was called the PPDAC. While the acronym is really confusing, it really stands for Problem, Plan, Data, Analysis, and Conclusion. And that's effectively, that just gave it more food for thought. We, we also learned that it is called Statistical Inquiry Circle because this was kind of a loop and we had to go over it again and again and kind of take a different problem every time and try to effectively solve it or arrive at a conclusion effectively. So the way it used to work or the way it effectively works is we come up with the problem, we really define the problem. So for us, the sales was the problem because our t-shirts were, we needed to know how to do better, how to improve our sales and things like that. So we effectively wrote it down and what the framework advises us to do is we need to figure out what questions are we trying to answer, what variables were involved, and who are we talking to? Are we talking about guys or are we talking about girls? Was there a certain specific relationship between them? Were they falling under a different demographic? Was there some sort of an economic indicator like the colleges whose students whose parents were rich were more inclined to buy our t-shirts and those kind of things. So the problem stating was the first thing we had, was the first effective problem, which we had not done. We were effectively looking at it inverted. We were looking at conclusions first instead of writing out and laying out a problem. The second step, the second challenge was to plan out, which is plan out what we were going to measure and how we will measure it. And then there was a lot of data. Then how do we collect the data? How do we sample it? How do we record it? Since the sources were too many, there were different e-commerce providers who were sending us data, and then there were manual providers who were FTPing us data. We needed to understand and come to a ground level and plan it as to what would be our starting point, what would be our system of record, as we like to call it. And then we moved on to data itself. The problem here was to collect the data. In the previous step, we had defined what are the sources, how to do it, how to analyze it, how to sample it, and stuff like that. But now we needed to really physically collect the data. And we should be able to display it very clearly, because if we get the data and if we cannot see it, when I say see it, it's in some physical form. It could be over a query, or it could be in some platform, or it could be some tool which is understandable and interpretable by a human being. That's what was important to us. So that allowed us a way to compare similar data. For example, data coming from e-commerce provider one had additional data points compared to the e-commerce data provider two. They were giving me more parameters such as timestamps of the transactions, which made our data time series instead of only pure transaction, which was just raw information to us, and it did not give us any cyclic information. These are the sort of problems we dealt with when we looked at the data, and we looked at the steps of data cleaning. So what we did is we defined the mechanisms of how to collect the data. We collected the data and we cleaned the data, and then we passed on the data for further analysis. In the analysis phase, this is usually, this can be correlated to the modern world EDA, exploratory data analysis, or modeling even, for that matter. Now, this is analysis of the data. It doesn't specifically say what to do with the data. It's just specifying that you evaluate and analyze the data. So we kind of sorted the data. We filtered it. We drew graphs around it. We did statistical tests, like, was my data distributed well? Was there a certain inclination towards a specific group of people, or a specific kind of transaction, or a specific kind of t-shirt, for the matter? So effectively, the analysis step kind of helped us write observation, look for patterns, make a hypothesis, and be ready to answer certain conclusions. So far, we were able to define the problem, plan around it, collect the data, clean the data, and analyze the data. And things were looking really good for us, because we now had a much better understanding of what to do. And then effectively, when we went on to the conclusion state, this was the really hard-hitting step, and where we had to see that the problem that we started with, did we correctly answer it? Because a lot of times it happens that, and this is very common with us when we start looking Wikipedia articles. We start with something, and then after 10 minutes, we have 20 Chrome tabs, and we forget what was the original intent. So the conclusion must solve the problem that we started with. So what's the answer to my question? And then how reliable is this answer, and why? Is it because I did it, or is it because the graphs tell it? Is it because the data tells me, or is it just my intuition? So it could be all of these challenging questions that we need to see and debate to come up with a validated conclusion. Now, hypothesis fitment, how does the answer fit with my hypothesis and where does it lead to? What additional insights can I generate? Can I do another PPDAC cycle to see a new hypothesis, or a new problem, or a more detailed insight into the current problem? And how would we do it different? What we collected the same data. What did we miss? What could we change? So effectively driving out conclusions and interpretations, and then laying out foundations to another cycle. Also figuring out in retrospection, what was the limitations of the investigation? Did we do anything wrong? Did we collect the wrong data? Did we need to collect more data? Those kind of things are effectively what we did here. So going back to a company, what was happening with us is, with a lot of our online platforms and e-commerce providers, is a lot of people were browsing our t-shirts. So let's think of the people as three categories. one set of people who's just browsing. Like out of 100 guys, 50% they're just browsing. They're not buying, they're not doing add to cart. 30% of the folks are adding to cart, and the last 20% are adding and paying. And that 30% people is immediate revenue. Even if I could convert 5% of it, I get direct revenue. So the goal was to improve my funnel effectively across the whole cycle, across the whole browsing, adding to cart and payment cycle. So we took PPDAC and we decided that we'll solve this problem and we will do targeted marketing campaign to those uniquely identified customers. Now, the problem was how many of my customers are adding product to the cart but are stuck at payments, and who are they? Because the number, how many, is a question that is just it's a count, it's a percentage. However, it still does not tell me who they are, and unless I know who, then I will not be able to figure out what to do with them and how to action them. So actionable analytics is what is important. So the first PPDAC cycle, we figured out how many, and then in the second one, we figured out who. Now, just to look at as a thought exercise, the problem was how many of our customers are adding products to the cart and are stuck at the payments. And then when we went on to planning about it, we realized that we needed our sales data, we needed our customer information, we needed payment platform information. Because the sales data is just giving us one part of the picture. It was helping us answer how many of them. But we have to combine it with as to who they are and to come up with actionable insights for the customer. This is the customer ID, this is the phone number, or this is the email address of the person whom we need to target. Also, we realized that was it a customer challenge? Is a customer facing a problem in the payment? Because we were just doing one or two payment platforms and there are tons out there. So we wanted the customer to feel very easy and to feel at home when he does or he or she does payments. So we also plugged in the payment platform data, which we had easily available to figure out the whole demographic. So we had all the sources very well defined. We wanted to look at sales data, we wanted to look at customer information, and we wanted to look at payment information. Then we decided actual system behavior, actual system integration. How do we integrate with the e-commerce platforms to pull sales data? Two of them were giving me REST APIs, which are great and the most modern way of integrating with services. One of them had very, very large data, and he was using a term called big data, which we had no insight about and how to get the data. He kept talking about something about change data capture. You will get data changes as in when my systems are updated and whatnot. But we did not really followed it because we did not have any experience with that. And then there were some providers who were just doing data manually, who were just looking at data from a manual sources. All right. And finally, we had an internal CRM tool for mapping, which was effectively helping us find who those people were and what they were doing and exactly identify the phone number and email address of them once we plugged it with the e-commerce data. So these different data sources was how we used and integrated to. And then the problem was to effectively come up with hypothesis, effectively come up with ideas, analysis, and that's what we did. We evaluated the trends and we figured out who those people were and how were we targeting them in the current paradigm. What are the challenges they were facing? Was that a payment problem or was it just a customer who had a habit of adding into his cart? And this led to another detailed discussion around a feature which we called as a favorite list, because people really didn't want to buy everything. They were more doing a like window shopping and they really wanted to make things out as their favorites for later purchases. And that sort of an exercise evaluation of trends enabled it. And finally, we were able to do targeting marketing campaigns to the identified customers for pixelhoodie.com, which is how we solved our problem using a framework. So that's a very conceptual and a simpler way to describe. Now, this is not an infrastructure perspective yet. We'll be talking about in the next, as we move forward, and we'll be talking about the system attributes. But this just describes a flow of looking at any business problem. And it could be a startup, it could be a very large scale enterprise, but the way we deal with problems would effectively remain similar, if not the same. Moving on, let's take a question break. Said, do we have any questions so far? How are we looking good on time?
Yes, so we have almost 1.5 hours, left with us. So we have two questions, and I think let's take them.
Sure,
So
let's do that.
first question is, we talk about scalable systems. What kind of scalability, according to you, are we capable of?
So when we say scalability, I think we'll talk about scalability in a much larger detail. And the word scalability itself talks about, in the infrastructure sense of it, talks from 2 points, vertical and horizontal, where we can grow in both the dimensions from a system. Scalability also in terms of business would be that we have a business idea, how do we grow it? And if it is just a go-to market scale, then systems do not play a lot of role. But if we are dependent on systems, then we need to understand the aspects I'll be touching upon, like how are they deployed, how are they healing, how are they responding to failovers, how are they reacting to different situations under load and things like that. So the quality attributes is the next section of our discussion, and that's where we'll focus a little more on the scale part of it, on the technologies that power scale, things like Kubernetes of the world. All right.
Yes.
What's
So
the
there is
next
one more question, Akash. So, is there any way we can automate all of this requirement gathering?
So requirement gathering, that's a very interesting question. Now, uh, problems are effectively thoughts. They are effectively ways in which people think, and the skill set that is usually associated is a business analyst who does that, who has an ideation discussion, who talks to people, who talks to business owners, and translates it into a language which is more system friendly. Now, there's some degree of automation possible if there are already existing systems, if the data sources are already available, if we are already generating some insights. But if it is a greenfield operation, it is effectively a human conversation where two people or a few people need to sit down and talk about the problem and then derive it. And each of them will have a different skill set. You will have a business owner, you'll have a business analyst, you could have a technology special subject matter expert, you could have a functional subject matter expert, and in that landscape, you'll typically have an architect who will help moderate all these discussions and let's say help come up to some kind of a conclusion is if a specific set of requirements are actively meeting the needs of the business. So the direct answer to that would be automation for problem creation or requirement gathering is a more humane way right now, and that's how effectively way people think. But the frameworks effectively helps envision it. Certain frameworks or certain frameworks do give tools to effectively document these discussions, and that's to the extent at which they goes. And then as you go in deeper, you do requirement modeling, you do data modeling, then you do class diagrams, and you do code generation. So there's a level of automation possible after that. However, the initial problem formulation, I still believe is best done by human beings.
Yes, I think that would be the right answer for this question. So, I think Akash, we are going great till now. I mean,
Okay.
the way you have set up the stage by making up a setting up a company and explaining it how it will be scalable. So I think it's going great till now. We're having a great experience.
All right, thank you. So far we have looked on framework, and there's one more very popular framework, which is called Cliff DM, which also pretty much helps break the process of data mining into 6 different phases. It's like business understanding, data understanding, preparation, modeling, evaluation, and deployment. Now, these frameworks effectively just help us talk about things, and a larger part of scalability is understanding the need and the use of these frameworks. The technology that powers is still available. It's readily available. It's very democratized, but the need and the use of these frameworks is, and that really allows the best users of those technologies. Now, moving on, we'll be talking about few of the non-functional attributes that go on into designing such systems. Now, before we do that, let's understand and define what a non-functional and a functional requirement is. A functional requirement is effectively what the system is doing, what it is performing, what it is, the set of operations it is doing. So for a banking system, your ATM machine is effectively helping you take out money. That's a functional requirement. But if an ATM machine starts to give out money every 20 minutes and freezes after every transaction, that would be one hell of a bad ATM machine. So in order to do that, we need to know that we should put the horse before the cart, which is the quality attributes of the system are the behaviors, are the parts of the system which drive the system per se. The functional aspects of the system, the different functional aspects. It could be again payroll processing, banking, it could be report generation. All of these aspects help drive business value and user. So from a system design perspective and purely from an architecture and infrastructure talk perspective, from this point in time perspective, we looked at a business problem of a functional nature where my sales was decreasing. Now we are going to look at the different quality attributes of the system, which is non-functional in nature. And there are really a lot of them, but we'll start with just a very few of them in the essence of time and the data related conversation that we're having. So let's go through four of them to begin with, and we'll look at one of them at least in slight more detail as to what I'm effectively trying to get to. So speed, volume, cleanliness, completeness. Speed can also be thought of in terms of frequency of data, or it could be just at the rate at which how fast or slow the data is flowing in. So effectively what these are quality attributes of the system. Now, nobody really, when you go and define a sales problem, I was not looking at the speed at which the report should be generated. I was only saying that I want to know all of those customers whom I need to action upon to be able to send them marketing insights or marketing promotions or marketing campaigns so that they could take the product which is in cart and actually pay for it. I just looked at the functional aspect of it. If I would have thought about that, do I need this in real time? Would it be possible that the moment a customer adds a product in the cart and leaves it there for 2 hours, I send a marketing promotion? So this is a more real-time scenario. An alternate or a batch mode of operation would be where we get all of that customer data every month and we figure out who were those people that kind of had the data in their cart, and then we figured out their email IDs and then this blast and marketing campaign. Now the accuracy of this marketing campaign is to, as you can imagine, worthless because we are looking at a month's old data and we are not actioning upon the latest data. So actioning upon the latest data is becoming need of the hour, and it is extremely valuable that we evaluate, look at the customer data, the trend, the behavior, and feed it into an analytics pipeline in a near real-time fashion, if not immediate scenario. So speed is very important. Now the alternate dimension, the batch mode of operation is still useful. It could still be a good data mining exercise where I look at an years of data, an year worth of all my customer information, and then I figure out that is there a specific customer segment of probably in a certain age or in a certain year of college or a certain gender demography and then age or an economic indicator that is just adding data to the cart and is effectively not paying for it. So those sort of insights are also useful. So the need for talking about speed is effectively important. And ideally, when we write our functional requirements, we must have a column which says, is this a real-time or a batch requirement? Is this transactional or more analytical in nature? So the problem of demand forecasting that we looked at, there could be short-term demand forecasting, which is we do a weekly demand forecast to manage and replenishment of stocks in the warehouses and whatnot. But we could also do a more longer term 6 months, monthly, or a year-long forecast, which are more targeted towards strategic planning of the company. So speed of data ingestion, speed of forecasting, all of that is effectively important. So talking about speed is needed. Moving on to the second one, which is volume, and this really has been a very popular buzzword with the big data coming up and occupying a large space of the whole segment in the past 4 to 5 years. This effectively is how big or how small the data is. I was looking at the large data sources on Kaggle yesterday, and I realized that it was very difficult to find data sources worth more than 10 GB of data. So effectively, the data that we look at or the data that we deal with in a more day-to-day fashion is smaller compared to larger data sources, big data sources. And small is typically very debatable. How small are we talking? Are we talking megabytes of data, or are we talking kilobytes of data, or are we talking terabytes of data? Now, we could also have a different scenario where we have data coming in at a really fast pace. For example, an IoT landscape where the sensor data is very, very small, probably bytes of information, but accumulated over a month, it's huge. So volume becomes another dimension to look at along with speed. So describing how big or how small my data is, and not in the sense of the big data word, big or small in the sense of gigabytes or terabytes of data, and what frequencies of data do we need to accumulate to reach at that this scale is effectively we need to talk about when we again design a system. And the underlying idea is the system should be able to address growing data needs. So if I'm to integrate with 5 more e-commerce platforms, my analytics pipeline should not shake. It should still give reports at the rate at which it is giving, most likely within the time at which it is giving, though that's very difficult thing to achieve. And also the responsiveness of the reports must not be impacted in any way. So that is the impact that volume has on your whole pipeline, on your whole setup. So volume is the second thing that you should be looking at when we are dealing with data. And as we looked initially in the first 2 slides, that it is constantly growing, data is growing. Cleanliness is a virtue of data. It's more to do, this dimension is much more popular, cleanliness and completeness, in the recent worlds. In traditional worlds, we had ETL systems, which was kind of taking in, transforming the data, cleaning the data, massaging the data. The intent is to free the data of garbage, and it could be NANs, as people in Python world know it, or it could be just gibberish information. It could be spaces, and this impacts the interpretability of the data. This impacts evaluation of the data. This is where we look at data and see that, do we need to do imputation? Do we need to perform some statistical operation, or do we need to do some remove a column and things like that? So cleanliness of the data is very important. This also ties to the structure of or the format of the data in which we are getting. Structured data sources like CSVs, or for instance JSON, they are much more clean. They have a structure. It's very easy to find out that a data source has a missing value or something. But for unstructured data source, cleanliness becomes a very, very large step. We kind of, all of us, when we deal with NLP problems, all of us are used to doing text pre-processing, where we remove punctuations, we do lemmatization, we remove capitals, we remove numbers, we remove I don't know, exclamations, question marks, and things like that. So cleanliness of the data is important, and again, this is an aspect we need to evaluate, and it is already done when we do an EDA exercise of things. And the underlying idea is that my system should support those actions that data scientist needs to take in order to clean the data. So we are effectively designing a system that enables all of those things. It needs to enable data scientists. It needs to enable production. We cannot have one work in isolation, and we cannot have 5 different teams performing 5 different rules over the same data, even though it could be a very large team, but there should be a sense of cohesion between them. Completeness is a virtue which is more functional in nature rather than non-functional. It effectively impacts the usefulness of the data. How complete is my data? How good is it looking? How much it helps me solve the business problems I'm trying to solve. We could be collecting news articles for a sales problem, and that uh, could be useful or could not be useful for that matter. I mean, we cannot intuitively or directly say that the news articles have no correlation or no inclination towards the sales projection. They could very well be. There could be weather indicator. There could be economic indicator apart from the core sales figures or core marketing figures that you're looking at. So building all of that is an attribute or a non-functional aspect, and the underlying framework of machine learning it needs to enable it. Now, moving on to a little bit more concrete or a more dimension of data, which I needed to focus on speed, which is the rate at which the data is flowing, and this kind of one is one of the most important things we look at. So we have data in different formats and different sources. We have data in files, we have data in blobs, and these are the batch data sources which operate at a certain frequency, and they could be nightly, weekly, monthly, and things like that. And these are the data, they could be large volume for that matter, and that's the reason we have chosen a batch mode of operation. Or it could just be that the systems are designed in a way that they support batch transfers. These are legacy systems, these are old age CRM systems, these are mainframe systems and things like that. Then we move on to a more little faster pace, kind of a bicycle where we have transactions, APIs, web services, and those things which are much more faster than a file transfer. These are near real time. These are real time in a lot of scenarios. They are push based or pull based. They are event driven and things like that. So these data is, again, it is important to categorize it to be able to understand the type of data we are dealing with and design the architecture for it. Now, moving on, we move on to some really fast data, fast streaming data, IoT data, which is and in certain use cases warrants use of some specific protocols, like IoT use cases often imply MQTT protocols, which are low latency and low network and consume a very low bandwidth, which allows sensors to keep transmitting data at a very fast pace. And these are usually hundreds of thousands or millions in every minute transactions. Now, dedicated architectures exist to support that. In this slide, we are more focusing on scaling from the central part of this, which is the APIs, web services. But we'll touch upon the streaming and IoT aspects of it a little bit. And now moving on with the functional, with frameworks at hand like PPDAC and CRISP-TM, and an understanding of non-functional requirements as to what we have. We have now piled up an understanding of how to solve a problem and how to look at different quality attributes of a system, which naturally leads us to the questions around machine learning system design goals, which are what are the things that a machine learning system must have in order to be really easy for implementation. And I like to think these couple of Dilberts are, I found them in the past few days, and these are really interesting. We often come up with different set of jargons. We have cloud, we have in-memory computing, as Mr. Dilbert is trying to listen from his boss, and we have scalability, we have cloud. But why do we need to effectively talk about it? So the idea is that as the data grows, so does the need to smartly process it and be able to generate actionable insights as we started talking. And a pure technology implementation makes sense in an R&D landscape. While when we work in a business application, it is important that we understand how to leverage these technologies and also understand when not to use them. What are the things it is not offering? Because most of these, even though are sold as one-shot kill. They are not really. What these are just pieces of the puzzle that needs to fit together nicely. So it's important to understand the need for these technologies so that we respond to the changes nicely and also grow our digital assets. Now, moving on to a section around the problem statement of why we need to talk about system design goals a little more in a machine learning landscape. And we often start with the prototype, much like the stick figure that is there in this drawing. And then we enhance it. We keep on enhancing it. And we think we have enhanced it. But what effectively happens is that we have incorporated a lot of bugs in the system. The most coolest aspect of machine learning, which is modeling, allows data scientists to play with statistics, to play with graphs, charts, numbers, ROC curves, AUC curves, and all of those things. But again, these are these are responding to the analytics problem. This is not effectively solving, it is not really the best way to solve the overall system paradigm, the overall challenge of serving a machine learning model to an end customer. So the idea is that the data scientists, the people who effectively evaluate the data, the model, or the business analysts, they typically work in a Jupyter notebook landscape, which is kind of designed for more quick feedback, data exploration, and do a quick train and test in a sandbox environment. But really, if you even execute 10 GB of data with pandas, most of you would have experienced that your Jupyter notebook fails or it kind of freezes in the very least, unless you have more than 32, 16 GB of RAM on your machine. Now, while this idea is a great, the notebook environment is great for building prototypes and targets faster time to market, these do not make it production ready, because if the data itself is 10 GB and your code is, your notebook itself is crashing, how do we anticipate that we'll get thousands and millions of users and will not get any latency? Excuse me. So effectively, are we production ready, or are we driving our systems that are built around bugs doing it? So that's the whole idea. That's why we need to move from this. And a very easy notion that is popular is, yes, we have built a model. Now we wrap around it a Flask library and build an API, and that's it, done. We are ready to go. But that is not the case. Have we thought about load balancers? Have we thought about API gateways? Have we thought about security? Have we made sure that users are authenticating and they don't have a direct or a download option of to our model? So those kind of behaviors and system-driven things is something we need to plan around in the whole landscape. So moving on, we'll do a quick check on the system design aspects. And again, this is not the exhaustive list of goals that we need to address. These are just thoughts that we need to build around, much similar like non-functionals. So four of the most important ones that I think is the system must have low latency, which is effectively the observable speed of operation across the platform. Now, when we start documenting our requirements in Jira or in Rally or whatever task management system we do, and we model, I have never experienced or seen a parameter which says that this model is designed to serve 10,000 users. Or this API is designed to address a model or consume a model which is going to serve 10,000 users. And model size could be 5 GB and we'll go again and happily serve it. But inferencing takes 10 seconds and people are waiting in queues. People are waiting to be served by the machine learning model that is just giving them no value at the point in time. For example, let's look at my problem again. And if I have 20 different kind of t-shirts, and I have designed a system, an online system where the t-shirt categories are being recommended, and the model size is extremely huge. It's like a GB. It takes in all parameters of the users, and it kind of evaluates it on the 1 GB model file, and then tells which t-shirt size to show to the user, and that's what is displayed. Now, if I go ahead with this design, what will happen is my users will see some sort of a buffering logo, or they'll have to wait for some time. they'll observe slowness on the platform, and anything more than few seconds, we lose users' interest. That whole exercise is futile. That serves no purpose, because if we have incorporated latency into our systems, if we have incorporated latency into serving effectively a model to the user, that is lost. We all live in a very fast internet speed, and data is cheap. So when we scout on platforms like the Amazon and Flipkarts of the world, we are constantly fed with information. Even if it is an internet switch off, we see the Jeff Bezos dogs. So it is that important to keep your customer engaged and make sure he or she does not feel latency or is connected to the platform. So thinking about latency when working with machine learning models, and because of the nature of compute requirements that they possess during inferencing, is becoming very important. Also, if we are training and retraining models, those scenarios must be factored in. We must be serving the latest version of the model instead of kind of doing a retraining and making a user wait for some time so that he or she can get the latest model. The second part to it is it should be message driven and non-blocking. This is an extension of the first one. Even if there's a latency in your system, even if for an unavoidable circumstance, we had to incorporate a degree of latency because this is the best we could do at this point, which happens a lot. We need to put a non-blocking design, which is to say that some piece of information, it could be an older model that is still serving the customers, it could be a simple message, or it could be a completely a failover strategy, which is more like a hard-coded thing, is sent to a customer. So the design effectively should be non-blocking. It should be built around messages. It should be event-driven. Also in a more RESTful context, or in a more API-driven context, there must be information that is usually pushed onto the platform, and we should try and avoid as less API calls as we need to, so as to enable the non-blocking design, or an event-driven or a message-driven design. Again, there are various architectures to it. We could do pub sub, we could do push notifications, we could have a caching mechanism implemented, which is kind of reducing some latency and incorporating a slight degree of non-blocking nature, but that's all to balance. All of these things are effectively discussions of balance. Moving on to scalability, again, vertically and horizontal scalability, vertical being that we should be able to add more machines of the same kind, and horizontal being we should be able to increase the computing capabilities of our own machine. Now, this is with the elastic nature of cloud, this is much more, these words play a much more prominent role in cloud, and with containers and Kubernetes, they are also growingly becoming very popular, and deciding what sort of infrastructure is to be picked depending on the services, or just instantiating another application or a compute resource for my app. Moving on to coupling, it is an attribute where the systems are decoupled. They are effectively designed around loose coupling. That again, microservices word is very popular, and containers help achieve some of them. We isolate our application units, we isolate our pipelines, we isolate pieces of functionality that we need to achieve. For example, evaluation frameworks could be kind of different from training framework, and the only thing shared between them should be results. So that's a very, these are now, again, some thinking points, and the right balance of them is what is needed when designing on a machine learning or any scalable system for that matter. A little more deeper dive into it, what happens is more often we are scouting for new data sources to improve our model in the system. And then we realize that our integration capability is not nice. We are focused on building a system which is great at model, which is great at ingesting one kind of data, let's say CSV or an Excel or a REST source, and the entire thing is coded in one single unit of application, kind of a monolith. And now we have to go plug onto another data source, which is changing at a much faster rate and we need to implement a CDC, which is change data capture mechanism, uh, our system doesn't allow that. So ease of integration must be factored in when we are doing system design. Distribution and scalability, a lot of this comes from the world and the need to run our code in a multi-clustered architecture. For example, a lot of you must have worked with PySpark and pandas and scikit-learn. Now, scikit models and pandas, they are inherently sequential in nature, and they needed to be run on CPUs, probably with large compute. So they kind of go in a queue and run your code in a pipeline kind of way, in a sequential kind of way. But if we were to look at Spark, which enables more parallel processing, it's very difficult to port one piece of code or a model from a Scikit model to a Spark model. And yes, it is possible. There's some sharing happening. There's some data transformation happening. You would take a pandas data frame, you'll convert it into an RDG or a PySpark data frame, and then run it in a clustered environment. But these are all makeshift. And had we thought of the non-functional attributes first before jumping onto modeling exercise, we would have inherently started with frameworks that support distributed processing. So that's the key message here, to think about distribution and scalability. Flow control is another important aspect, which is to effectively look at architecture and to effectively handle scenarios where my system is getting data at a much faster rate and I do not have enough time to process it and store it. And then there are specific pipelines designed to handle that, streaming architecture, kind of the Kafkas of the world that are very popular nowadays. Also, flow control is important when we have different parts of the system to orchestrate, and we need to run one piece of the code after the other and things like that. So there are a lot of frameworks around it. There are cloud native frameworks like Kubeflow, there's Apache Airflow, there's MLflow and things like that that enable flow control into our system. Moving on to a little more thinking exercise and going back to our pixelhoodie.com platform, these are the questions that we really thought and we kind of answered it. So the first one is how much of a latency while my user is getting while interacting with my platform. So the latency effectively, as we talked, is this observable slowness and behavior across the system. Then the second one is how easy or difficult it is to manage a new or integrate a new payment system. Now this is coupling and integration. Remember when we talked about a lot of my people are adding t-shirts to the cart, but they are not paying for it. And part of the reason was I did not have the most popular payment platform. So how do I integrate with it? How do I make sure it is easy to couple and easy to integrate with such systems? Does my authentication system nimble enough to adjust the needs of the provider? Because they would be dictating the terms of integration most of the times. So we need to be, again, looking at the most popular frameworks in this. We need to be thinking about OAuth and not some proprietary way of doing information. We need to embrace single sign-on and things like that, specifically on the authentication side, which is a very, very, very common challenge when we do such integration, because payment systems are really, really tightly built around authentication, and that's the framework they'll support. We'll have to just adhere to it. So the best we could do is make sure that our system doesn't block those integrations in a way. So a study, even if a descriptive study initially, is good to design such a system. The message-driven non-blocking design kind of says that is my system spending time in waiting for a response, and are my users actively and happily seeing all of scalability benefits, like if I have a peak load, did I do good? For instance, just before semesters, nobody wants to wash their old t-shirts, and they were just keeping on continuously buying my t-shirts, which is never wash and never do it. So I had a lot of load. So was my system effectively scaling correctly, both horizontally and vertically? Did I impart functionalities, or did I incorporate design elements into my system which blocked scalability? That's the thought I need to go. And finally, all IT systems will at some point find that they are into a failure landscape. Biggest of cloud providers have seen disasters. It could be natural or man-made, but what we need to understand is fault tolerance is a capability and one of the most important non-functional aspects which we need to address, specifically in dealing with business critical and management systems. Does it support automatic recoveries? Does it support checkpoint restart? Do we kind of have a new instantiation possible when we are dealing with such systems? So these are the thinking exercises that we did. Now at this juncture, we have thought of systems, we have thought of system design goals, we have looked at some problems that are again, and all of these problems, all of these systems questions needs to be asked when we are in a scale landscape. It is absolutely okay to go without it when we are serving, let's say, a few hundred or thousand of users, or we are doing a proof of concept. Now, this is a good software architecture. It's a good idea. But again, if you're building a POC or a small product initially targeted at a low number of users, we need not worry about scaling vertically or horizontally or message driven or failovers, because most likely we would have chosen a platform which gives some of those things inherently, and we can rely on those happily without worrying about these in a system design. But when we deal with enterprise systems, we definitely need to think about these things, and we'll talk about some aspects like data center switchovers and things like that in few later slides to come. All right, moving on to questions. I think the baby with the questions is back. So, Sid, Nishcha, any questions that we have so far? How are we doing on time, by the way?
Yeah, so we are, we have completed for 1 hour. So we have quite a few questions. So let me.
Okay, let's take them.
Okay. So the first question is, how do you evaluate non-functional requirements and how do we go about measuring them?
So that's a pretty nice one. So non-functional requirements, the measurement part is something important, and I'll just come to it when I say how do we define it. So the definition of non-functional requirements varies in landscape to landscape and problem domain to problem domain. Depending on the kind of functional problem, the architect and the business analyst should collectively get together, evaluate the more landscape. Is this a big data requirement? Is this a batch reporting? Is this a transactional system? Is this an analytical system? Are there legal constraints? Are there security constraints? Do we need to worry about some specific technology restrictions, deprecated frameworks? These are the non-functional aspects, and some of these should be and most of these should be documented with your project charter or program level documents. And the way of measuring is there are some tools to measure the more visible aspects like latency, number of users. You could be using tools like a load and performance testing tool, which like something like a load runner or a JMeter, which will kind of simulate the same load onto your system and gives you a benchmark as to how much your CPU or memory is utilized while serving the target or the threshold number of users. And this could be a starting point about thinking, what is my current benchmark? When I did a load testing, this is what I got as an answer. And the next step would be that what is the desired limit that business wants? Because optimization is a very, very hard problem, be it machine learning or in system design. If your load and performance testing tells you that your APIs are performing well within 5 seconds and your users are happy with it, take it, accept it. Because making it 1 second is going to kill your engineering pipeline. You'll be spending a much larger amount of money in beefing up that infrastructure. So measurement could be done by active measurement, numerical measurements can be done by load and performance testing tools, load runner, JMeter, and documenting them. Other aspects of non-functionals are documented in a more traditional fashion, like tables and charts and your matrices, Excel matrices, something like, do I need to store or checklists even, do I need to store the data within Indian boundaries? Do I need to be GDPR compliant? What other additional checks I need to do? So these kind of things are, again, go in the form of a checklist. And it's important, again, that all of these things stay together. So that's probably one answer to that question, Nishchay.
Yes. Yes. So now we have two questions by Gautam. So he's asking, why is scalability important for machine learning, and how can we know that we are building a efficient machine learning pipeline?
Great question, Gautam. So, the how can we know that we are building a scalable machine learning platform? I'll come to that when we talk about data pipelines, which is the next section. And why is it? It's really that when we, as data scientists or as machine learning practitioners, the word itself, machine learning, implies that we are making a model and we are making sure that there's some kind of learning happening from past data usually, or it could be probabilistic, which is also a little bit past data. But what is effectively happening is that my system is building an understanding of the behaviors, and then we are trying to serve it. But this is not the overall landscape. The overall landscape looks like you have data coming in from 10 different sources. And then you have business users, for example, let's take my fictitious company. You have users who are accessing the platform. They do not know whether it's a machine learning model that is serving me or it is just an intelligent system. So one piece of system is the machine learning aspect and the model. Another aspects are just traditional API designs, traditional engineering problems, your software design, your database management, your data schema management, your API structures, your cache management, your security management. All of these things are inherent part of the system. So if I fill probably if I fill a completely AI, if I fill a slide with a boxes with 20 boxes of, let's say, system design elements, probably 25% of, and this is an AI system, probably 25 or 30% of them would be centered around AI. But the rest would be to build the data from previous steps, from previous systems, from other systems, also from serving APIs to my users, supporting integrations like payment platforms and things like that. So that's why we need to build and think about machine learning at scale, because doing things in an isolated way is a great way to learn, but doing things in a scalable way is the way to achieve business value. And how do we know about that we have built a machine learning model? It's very simple. If your targeted user base is able to successfully reap the benefits of the AI system you have built in a easy to use fashion, and the usability requirements or the user experience requirements are met, then you have successfully achieved it. Because as long as the user is happy, it will not matter if you are manually taking all the numbers, doing mathematics by all yourself and spitting out answers. So that's effectively a way to measure it. And if your user base is small, as I said before, it's absolutely okay to go about simpler things of the world. Just start small, build a pandas, skykit model, pull your data through pandas, build a skykit model, put a wrapper API around it, and start serving it. That's pretty much it. But then this is not a really scalable design. We haven't thought of the things that we just touched upon. I hope that answers the question. Mister, any more questions?
I think let's take this one more. So he is asked. So one person is asking that can you throw some more light on Crisp DM framework?
So crisp DM, like I'll have to go back to the slides. Let's just give me a second. Where were we talking about? So crisp DM, I think was started by IBM effectively, and I have just a note for crisp DM here. And this is specifically designed around data mining, and I was myself trying to think of whether to choose a crisp DM or PPDAC. PPDAC kind of is more generic. Uh, Crisp DM talks about the first step would be business understanding, then data understanding, data preparation, modeling, evaluation, and deployment. This is effectively focused around a data mining paradigm, a data extraction paradigm, and when we are trying to look at trends and behaviors. This is not effectively trying to talk about the entire system at scale, which is how do we worry about Kubernetes, and it doesn't get into the specifics of technology. It is just a framework which effectively prescribes a generic way of doing things. So that's a little bit about CRISP-TM.
I think that let's take more questions after, in the next question break. And
All right. Sure, good.
Thanks for answering.
Thank you. Now moving on, we need to go to pipelines. And this is where, from this point in time onwards, and probably the next 45 minutes, we'll be talking a little more machine learning and a little more infrastructure, or a little more specific than generic like before. So moving on to the pipeline aspect of it, traditionally pipelines involves overnight batch processing, and that's effectively collecting data, sending it through a enterprise message server or a message bus, and then processing it through a pre-calculated results and guidance or something like that, and reporting it probably to a dashboard. Now, this is a very common and general way of doing it. An enterprise service bus is a large vertical in your architecture diagram where all of different state data sources come and meet. It can help you do some transformations, and then your systems kind of consume the data and do MIS, which is management reporting. There are two different kind of modus operandi here, online mode analytics and offline data discovery. And effectively, the online mode of analytics would be more like real-time decision making. And the batch processing would be more like historical data trends or historical measurement of data in the sense of finding information or insights, a data mining problem per se. Now, the whole pipeline, and now this is one of the opinions of the pipeline. There could be different and it could be less or more depending on which company we are at or how our company treats it. So we have described it into 8 steps: problem definition, data ingestion, data preparation, data segregation, model training, candidate model evaluation, model deployment, and performance monitoring. And some of these are iterative steps, and we'll touch upon them. So data ingestion is effectively funneling all the incoming data into a data store. And this is the first, usually the first step in any ML workflow. The key point or the key message is that the data needs to be persisted without making any transformation. So it is important that we make an immutable data record and keep an original copy of the data, and that is absolutely untampered with. And the data can be obtained from different sources. It could be files, it could be obtained on request like a pub sub model, or it could be streamed from other services. And some of the very popular ways of you at this step or storing data in a data ingestion pipeline step is we could be using a NoSQL database or an Edge Hadoop kind of a landscape when the data is very large to offer some kind of a schema-less storage. And because the data is just as is, we are not doing anything with the data. So let's say if the data source is a different database altogether, we could be doing change data capture, CDC like Splunk or Apache Scoop, which enable capturing of data from different database by reading of their logs and scooping data on a periodic basis. Now, this is the data ingestion part where we have happily received the data that we needed to. We have gotten it into a immutable data store. Then we move on to a data preparation step, and the step 2 could be thought of as pd.read CSV, which is one of the most common things that we do. But this is more like in a larger scale. Now, the data preparation step is kind of the way when we say that once the data is ingested, we need a distributed pipeline which needs to assess the condition of the data, checks the format, checks the differences, incorrect values, missing values, skewness of data, probably an outlier detection and things like that. And this is kind of also includes some level of feature engineering as we think. Now, we would effectively extract the data from the data ingestion from the immutable data source. We would do transformation and we'll do some selection on it. Now, this is where the non-functionals of completeness and cleanliness come into picture, where we kind of evaluate and see what the data, what elements or what columns are to be selected for our model or for future steps. The data ingestion step has already seen the speed and the volume part of it. And I think this then continues across the steps. Then what we effectively do is we do segmentation, which is something which all of us are very familiar to. We split the database or the data sets into a test, train, or a validation split. There are different ways of doing it, 70-30, 70-20-10, 60-30-10, and that's effectively the larger is the training set, slightly smaller is the testing set, and finally you go for a validation set. And then you go to a model training step, which is the offline process, because this is the step where data scientists are typically working in a Jupyter Notebook landscape. And the schedule varies depending on the criteria of the application. It's also kind of dependent on the time as to when the model is getting trained, apart from the experimentation in real life. So the time and the event is important here. And then there's a candidate model evaluation, which is the final model, or let's say the best performing model of all the library of models. And different evaluators are used at this point in time. It could be F1 score, it could be a confusion matrix, or an ROC curve. And the model training on 5 and 6 steps effectively are back and forth. So we look at a lot of models, we come up with a candidate model and say, hey, this is good. No, not really. Then we go back to model training and then look at other models. And then we come up with a final candidate model, which is ready and which is the best fit model. And we have happily run it through our validation sets. Now is when we need to take our system or our model to deployment. And this is where we need to put a little bit of thought, which again will come across in few more slides. Now, the best model that is selected, which is offline, is needed to be deployed, and this is going to help serve the transactions for the users. Effectively, this could be served through a RESTful API where we follow an API first approach. We containerize and we serialize the model and effectively load it into some kind of in-memory store or a key value store where the model is always available and accessible by the API that is effectively helping access it. So that's the model deployment step. And finally, we go on to the performance monitoring. And it is important to monitor it because this again feeds back into the data ingestion queue. And the whole cycle is kind of iterative where we check and monitor how much deployment times we take, how many number of requests my model has served, and how much average and minimum and maximum and model serving time have we anticipated. Is my model really, performance of the model is one measure, but the serving time of the model is a very important measure in the system aspect. So while the data scientist evaluates the model for accuracy, the performance monitoring is effectively monitoring the model for real-time production use cases and seeing if the model is performing well or not. And also there could be a way to measure if it is performing well on predicted versus actual or observed result, which again feed back into the ingestion pipeline. Now to sum it up, a production-ready ML system will have an data ingestion queue, a data preparation queue, model training, and model evaluation and deployments. That's the road that we take typically for machine learning stuff. And yes, even though all of these things are possible in a Jupyter notebook kind of a sense, it is mostly different pieces, and think of them as different isolated units of softwares or isolated units of functionalities. Now, these pipelines, as it turns out, needs to be monitored because while we are behaving and working functionally with data, while we are serving some information to a user, our system or effectively our whole landscape, our whole software application is also generating a lot of data. It is generating information of the latency, it's generating information of traffic, it's generating information of saturation and errors, it's measuring the thresholds and the optimal uses of the system, all of which we need to collect, assess, and act upon. And this in itself is visualized and improved. So this is used for capacity planning, this is used for real-time alerts, this is used for monitoring the health of the system and overall paradigm of the software. So now we have touched upon a little bit on the non-functional aspects of it, looked at certain frameworks on how to solve problems, also looked at a machine learning pipeline. And now let's try and jump towards a more detailed oriented stuff around infrastructure and all cloud, Kubernetes, and things like that. And this Dilbert is very subtle, very uh, subtle. I think it reads, I need to know why moving on our app to cloud did automatically solve all our problems. And it does not solve the problem. So the response is you wouldn't let me re-architect to be cloud native. And what really is cloud native? And cloud native is often thought as just putting it in containers, but it really is not. Cloud native is a building approach in software development that utilizes cloud computing to build and run. And the build and run option implies that we use private, public, and hybrid cloud approaches. We use all different technologies in terms of compute, storage, networking, and all sorts of things. Containers and Kubernetes is something we'll just talk about, but just as a quick introduction, containers are isolated from one another and they could be thought of as bundles of softwares which are absolutely independent and run in isolation, and they can communicate actively through a well-defined channel. It could be a networking channel or it could be a uh, HTTPS approach or it could be an inter-container communication which is defined in the cluster. Now, moving on to some of the terms which Mr. Dilbert talked about. One of the important stuff is cloud. And effectively, and this is just a one slider on cloud, I could not do justice on this topic enough. So cloud computing is just democratizing information, or democratizing compute, democratizing system resources like storages, computing power, and the management of it is directly given to the users it is actively managed by a user. So anyone with a credit card can get a cloud, can get a infinite or near enough resources. Infinite would be a wrong understatement. Near enough resources to start any computing needs that he or she has. And the term is generally used is to describe the data centers that are available by different cloud providers. The most prominent ones are Azure, AWS, Google Cloud, and these are the ones that are always competing, and the services are predominantly similar in the sense. Moving on to a second term, which is also referred to in companies which have less understanding or less penetration into cloud, is an on-prem installation, where it simply refers to the infrastructure that the enterprise owns. And the infrastructure is a building, effectively, with there are 2 buildings or 4 buildings for this DR and stuff, and these house computers and associated communication to effectively manage the infrastructure. Now, there's a lot of discussions about benefits of clouds and benefits of a data center or a hybrid approach. And really, there's no answer to it. And really, there's no one shot solves it all. There's no one right answer to it. So some of the benefits of cloud is it offers nimbleness, it offers good flexibility, it offers immediate capacity without any upfront investment, while data center are beneficial for having a better control on your computing environment. Let's say if I want to control the technology stack, let's say if I want to have some sort of a cyber security layer, some sort of a performance and reliability layer to it, I would go for a data center. And very often there's a hybrid approach where cloud is used for a disaster recovery or a failover or a secondary data center. And a lot of startups prefer cloud because it's easy to get infrastructure. I think in my previous experience, I've realized that getting an infrastructure on-prem sometimes takes weeks or months, while in cloud, you could do it with probably a minute or two. So that's just a quick introduction on cloud and on-prem. Now going back to our problems, what have we need to take care of before the deployment? We need to worry about integration of different sources and transformation, like the older version ETL. We need to define the analytics store because the data ingestion is immutable, remember? We need to define and design an API that consumes the model, which again needs to be scaled, and it needs to be scaled to the needs of the user. It needs to auto-scaled probably. Implement cross-cutting concerns, and we'll talk about it in a minute. Define the deployable unit, log our model, and factor in retraining scenarios. So effectively, our pixelhoodie.com is still under development. We haven't really sorted it out, and that's the last thing probably we'll want to take a look in the end as to how the architecture looks like, overall architecture, and that would just be a recommendation. Cross-cutting concerns, as I talked upon, are pieces of systems or important aspects of systems which needs to be looked upon when we design a system. Typically, when we model or build any software system, we do not pay specific attention to configuration management, audit trails, scheduling, and these are the stuff that are thought of as operation stuff. But most of the times, this can cause a development impact. For example, notification, scheduling, and configuration management are really important. And if you want a user to have a notification when, let's say, a new insight for it is available. For example, my Google Photos, it kind of looks at all of my different photos and figures out a period of time and groups similar photo and gives me notifications so that I can see it. So that's a very interesting use case of the overall problem. And notification is a very important functional aspect of the system design. Logging is something which I wanted to pay a little more closer attention to, because most of the time in my experience, I've seen people using printf statements or print statements to track what is happening in the code. And that's okay for small applications. But we need to log effectively a little more than that. We need to be using specific frameworks for logging. We need to be logging data elements. We need to be logging our events, and that needs to go into a place where the log is easily accessible, not like the pirate we see, so that we could analyze those logs in case of failures. Because once we move things into production, we start the need for logs. And if logging is not present, then all we'll be left is a scenario where a system has failed and we would not know what was the data element that failed. Was it because of a rowdy rogue data element that just came into a pipeline somehow and screw things up? Or was it because of our code which was not able to handle a certain scenario? And logging is essentially important to support development activities as well too. Moving on to a little more isolation approach, and the most popular thing which is in software development and architecture right now, containers, and the idea and the core central theme also for building pipelines and microservices is effectively what we try and do is on the left hand side you see a traditional virtual machine or a system or a computer where you have a traditional OS, and the operating system has the operating system tools, the system D, SSH, kernels, and things like that. And then we install different versions, or let's say we have different software applications, Python, Java, Nginx, MySQL, OpenSSL, and then we have three different applications. Let's think these three applications, one to be Java, one to be Python, and the other to be a database or a web application for that matter. Now, what would happen is if I were to update any piece of my machinery inside, if I was to update the version of Java, an underlying dependency to a PySpark, because Spark effectively uses JVM, could get screwed. And what will happen is the application one could start working. And this would be a nightmare because I made no changes to that piece of the application. The only thing I did was update my Java application, probably my application runtime. The same is true for a configuration. If I implemented an HTTPS in my Nginx and some of the calls stopped working. Now this proves a lot of challenges. This poses a lot of challenges, and that's where containers came in. Docker is mostly interchangeably used with container technology. So Docker is used interchangeably. Now our container image is really just helping isolate the code. So there's the container Linux, there's the container system software, and all that my software needs to run are packaged inside a group. So imagine it like a blob or a circle, and it has everything that is needed to run my application. It could be a machine learning application, it could be the API, it could be a Nginx or a gateway or something like that. So what containers effectively help achieve in software architecture is isolation. And if we have successfully isolated a piece of code, the philosophy becomes build once, run anywhere. That's what Docker's mantra is. It effectively takes softwares, you can build it once and you can run it anywhere. You can move it interchangeably across systems. You can move it interchangeably across platforms. There's some incompatibility between Windows and Linux containers, but most of the times it works. Also, as the need for different networks grows, the depth of the network grows. I think Manu talked about the time series LSTMs are very deep networks and are really, really compute heavy. It could take days to train them on CPU, and hence there's a very growing demand for GPUs. So in some thought in our brain, I think we have understood that our computing requirement or our computing needs to be very, very different. The training needs are GPU oriented or probably a very large scale CPU, which is only going to be probably running once a month or twice a month, or when we need to train. While on the other hand, and this could be just a one application that is running for some time. On the other hand, my application like the APIs which are consuming the model, they need to be running multiple instances of them because as to serve different users, and they need to scale automatically on auto scalability scenarios. So what we need is probably a little more than isolation. We need to worry about how and where should my containers run, the life cycle and health of my containers, rollback and disaster recovery. How do we scale? How do we put in security? Can we have security vulnerabilities? Load balancing, because a container in itself is just a container. It is accessible through a single endpoint and is limited by the resources we give it. We and obviously we cannot allocate an infinite resources to it because it will result in a lot of money wasted. So we probably need, for all the different circles we saw in the pipeline, we probably need more than one container to run. One with a GPU, one that could scale multiple times, other that could take care of my batch operations and things like that. So what we need is something that could help me manage and orchestrate containers, and something that could update or roll back application without causing a downtime. Something that could provide me a high availability or a disaster recovery scenario, and something effectively that enables nice packing of infrastructure, best utilization of infrastructure. So some of these things containers offer by the principle of isolation, but for most of them, we need a technology which helps manage and orchestrate containers, which is where Kubernetes comes in, which is where Docker Swarm comes in, and these frameworks enable to run distributed systems resiliently. They can take care of all our scaling requirements, failover, deployment patterns, and more. They offer all the non-functional best picks that are needed from an infrastructure standpoint. For instance, service discovery, load balancing, storage orchestration, and using a Kubernetes is extremely easy. All you need to do is come up with a YAML file, which is probably 10 or 12 lines, which says, hey, this is my application, this is the compute, this is the storage, this is the VM I want to run with it. And these are my threshold. For example, if the CPU increases more than 100 milliseconds, spin up a new container and start serving from it. And it will automatically take care of that. So a lot of things that Kubernetes offers is just intuitive, and it is a data center grade information technology piece of hardware or a technology, sorry, not hardware. What Kubernetes is or does not do is it does not provide source code, and it does not deploy source code on its own. It's not a deployment solution. It's effectively, it supports different deployment solutions. For example, you could deploy it by SSH, you could deploy it using some cloud provided framework. You could deploy it more like a traditional way, use your Jenkins or Team Center for doing deployment. It does not provide application level services like data processing tools, databases, clusters, caches. It in turn enables them that you can have any of these tools inside your infrastructure. It does not dictate logging, monitoring, or alerting, but at the same time, it supports all of different those features. Remember the cross-cutting concerns that we talked about? One of the best or one of the most popular ones out there is Prometheus and Grafana, which helps achieve logging, monitoring, and performance and alerting at the same time when working with a Kubernetes kind of a landscape. It also does not mandate a dedicated configuration language. YAML is pretty much just an English-driven language. It's a really, really simple approach to things. It's pretty intuitive in its own way. And if we are building using a cloud provider, it's really easy. You could be using Azure Kubernetes Service or Elastic Kubernetes Service on AWS, and they provide very rich UI to come up with a Kubernetes cluster. It kind of hardly takes 5-10 minutes to come up with a Kubernetes cluster that is pretty much secure and that provides you all access endpoints and whatnot. Looking at the Kubernetes architecture from a very high level, and there's a lot of depth to it if we are into a kind of Kubernetes masterclass. But what Kubernetes does is effectively a master-slave architecture. So what happens is there's a the two boxes that you see on the left-hand side are rich UIs or CLIs through which Kubernetes can be accessed. And Kubernetes exposes APIs to API server, through kubectl commands, which are routed through Kubernetes master. And on cloud, these masters are effectively managed by the cloud provider themselves and are free of cost usually. Moving on, they are connected to different nodes, which are effectively VMs. So you are most of the times charged only for the virtual network that you use and the networking. What it in addition needs is a container registry where my containers are stored. So imagine all of those circles in my data pipelines, ingestion, preparation, modeling, etc., are different containers, and they're sitting in container registry. And we have told Kubernetes master that, hey, go ahead and deploy this. It would automatically enable them. And let's say for the API which is being served to the customer, we have set a rule that scale it when the load is high. And if the nodes allow it, it would automatically scale it. It would automatically come up with a new instance and start serving without any human intervention. It would start serving and it would automatically scale down to save cost. So once the threshold is achieved, it spins up a new node a new instance of a container. And once it is served, once the work is complete, it's going to spin it down and shut it down. So that's also a very nice way of auto scaling and managing it through very simple commands. It offers self-healing. For instance, if a container crashed, it would automatically try and restart it, again, depending on the scenarios that we would want to do. It also supports multi-node pool, which is a very interesting and a nifty feature. Let's say I want to run one container image as a GPU, and one of these nodes is a GPU. So node 1 is a GPU-enabled machine. Node 2 and 3 are, let's say, 32-core machine, and node 4 is like a small baby, like a 4-core machine. So each of them have different varying needs. The first one is used for training. The second one is used for day-to-day operations. And the last one is used for just the activeness and sanity check of the whole pipeline and the queue. So multi-node pool, auto-scaling, self-healing, logging and management, all of those things are available and readily to use with Kubernetes if it is given a container registry. So that's pretty much on the infrastructure aspect. Now, let's do a quick fact check, and I'm moving towards the end of my discussion. Let's do a quick fact check on how are we doing with pixelhoodie.com and what are the problems that we have solved. Now, did we define the services and the processes? Because we are effectively trying to scale. Now we need to think a little more beyond just selling to few people. We need to start thinking integration models, etc. So is it well-defined services and process? Yes, we got it from PPDAC and data pipelines. Do we have a deployable unit isolation? Containers are helping us achieve it, effectively Dockers. Do we have a container management solution? And there's more to it. Again, Kubernetes or Docker Swarm for that matter. Infrastructure, is it on cloud and is it on team? And then we had certain good people in our team, engineers, data scientists who are all working together. And the fact check is, this is where we stand. However, this is just the beginning. We need to also worry about load balancers, switches, networks, API gateway, etc., and things like that. For example, if my data is sitting in my own data center, how do I make sure I still leverage cloud? How do I set up networking between my data and this would be a step in data ingestion effectively. How do I make sure that my data sitting in my databases or my data store, which is on premises, is picked happily and moved to cloud, and the machine learning models are operating on it. So those discussions, those data movements, the networking setup, the security setup also needs to happen. And these are the things that we effectively need to start building upon. Now, moving on towards the last slide for this discussion, this is effectively a standard operating paradigm for almost a Kubernetes-enabled landscape. We have a bunch of awesome people. We give them a DevOps landscape, kind of a Git and certain tools to deploy, build, and deploy the pipelines. We give them a container registry to store their code. And again, they can interchange code and all that. It is connected to Kubernetes, which is connected to storage. And this is the whole setup. When we start moving things into real scenario, this is more the reality of it. So we have on the left-hand side new data elements coming on, which are parked or through gated or routed through an ETL, which is again stored in the data store, and that's fed or connected to Kubernetes. Now the piece of code or the containers that the models that was run and deployed onto Kubernetes is used to communicate back to the business owner through different analytics steps. It could be Tableau, it could be APIs, it could be dashboards, custom built. And these are this is probably just a direction on how to scale and grow with infrastructure. So the key messages would be to model your versions, model your software code, model your containers where you are pushing your new model, machine learning model versions. Come up with evaluation frameworks that are easily accessible by your team. And again, this evaluation frameworks might not be part of the production pipeline. Design your APIs for serving, design them for deployments, design them for ease of accessibility. Uh, Deploy your models, deploy your machine learning models in a very in a fashion that it allows easy accessibility, allow it to be in memory if possible, so that inferencing can be really fast. And then there are some frameworks which I think I touched upon before, like Kubeflow or NML Flow, and some proprietary stuff too, which helps achieve some of these things that we have talked about. So with that, I think we would I would take questions. Let's move on to questions. Mr. said, do we have any more questions?
Akash, we have quite a lot of questions now, but let's take a few of them. So
Sure.
the first one is by, so he's asking, how do I know whether my code is scalable or not? Is there any predefined checklist I should follow?
So okay, let me try and answer this. This is a really nice question. So how do you know if your code is scalable or not? First is, did we, before writing the code and before designing the way the code is going to be written, before the software design, did we have a discussion on the non-functionals? Did we define the target number of users this model is supposed to go and serve? We definitely looked at the evaluation step. We definitely looked at the model accuracy. But did we really look at the number of users and the volume of data this model has to serve? Or did we just took a sample and start working with it? Now, this is a thought exercise. A physical exercise is, if you have already have a code and you want to start at this point, I would recommend that you do a load and performance test of your app, probably in the most real-time, reasonably production, as close to production as possible. And with let's say, a good idea would be that the environment on which you run your load and testing is similar to production, or is it in a scale which you can map to your tests to. So for example, you have a 32 core machine in prod, so you go with a 16 core and do a LMP, load and performance, you see the results, and then you extrapolate it to double, and then you see and take it from there what you need to tune. Do you need to implement caching to manage your data better? Could you design your APIs a little better to improve the to and fro and back and forth of the data? Is your model being served too many times by the same type of request? If yes, then probably you would want to cache those results also. So those kind of thoughts needs to happen, and that's what engineering thinking is a little bit about.
So let's take another one. So,
Sure.
what tools exist for managing data science and machine learning pipelines?
So there's a variety of tools available. I think this also depends on the kind of infrastructure setup you have. And since I do not know that, I'll just touch upon what I said. So the things that you see here are pretty much good and sufficient to help you manage your data science environment. You would typically need a Git and a DevOps landscape to help to facilitate your developer code and prototyping and notebooking. You would need a container registry to store the containers that have been designed and developed. And yes, there could be some sort of a versioning across like development, production, staging, etc. You would need high compute environments to run your machine learning training jobs, which could be part of your Kubernetes cluster, because once you have too many nodes or VMs, you would need a software to help manage it. So Kubernetes could also be a tool, a platform underlying. And on top of it, you have frameworks like Kubeflow or MLflow, and there are a variety of others that could enable you to do all of these managing of these pipelines in a little better way. For example, the Optuna framework that Manu touched upon, can it be plugged with Kubernetes? How can it be injected? Because again, well, that all of these frameworks that we use or see must enable our own use cases like Kubeflow. Does it work with Optuna or does it not work with Optuna? MLflow, does it support legacy integration or does it only support REST API? And then you would also need to have some storage services like blobs or databases effectively to manage and store your transactional data. In an ML landscape, you would typically need a both a NoSQL key value based approach or and an RDBMS, because an RDBMS is nicely suited for a lot of reporting purposes. That's pretty much the set of tools I could think of.
Yeah, that's great, Akash. So let's take the last one.
Sure.
So you said Docker containers help in isolating different services, but how these different services running inside a container communicate to each other in a production environment?
Okay, so in a production environment, your architecture should be that ideally you have a Kubernetes cluster, and on top of it, there's an API gateway, which I did not touch upon. So one way is that you enable some sort of an inter-process communication, or sorry, inter-API communication across your cluster. So your API in container A should be able to call container B over HTTPS. So they could be making internal HTTPS requests. You could also be doing it through some data sharing mechanism. You could typically have a queue, which is, let's say your container A is just writing to a queue and your container B is reading from it. Now it depends on the kind of the data that you are operating. If HTTPS will happily work, REST APIs will happily work, and you could also not bring in authentication in between. You could do direct communication. You could plug it using some sort of a queue or something, and or if it is just pure data sharing or data access, you could also look at the core database of it. So there are different mechanisms, and containers inherently are not stopping you from any of the mechanisms that you have used before. So in the way that your software was communicating with another piece of your API, probably deployed on another VM, you will be using the same way most likely. If you had a service bus, you would use a service bus. If you had a gateway, you will have a gateway. Containers are not stopping you from using any mechanisms. The only requirement or the necessity which you have is the port on which you are making the communication needs to be mentioned in the Docker file as export port number. So the Docker knows that this port is what is going to be used for networking, and that's it. So that's effectively the answer to the question, Mr.
Yes. So do you want to take some more questions, Akash, or should we go ahead?
No, I think I'm good. I just have a quote to end, so we can do a more question now that pixelhoodie.com is up. We can do more questions. Let's do more questions.
Sure.
How are we doing on time?
So it's currently 1:23. We have approximately 7 to 8 minutes.
That's good. That's good. Let's take a slide, and I'll just need 1 minute for my ending comment. Let's take a few questions. Nisha, hello.
I'm sorry, I was on mute. So another question is, can you please explain how distributed data architecture works? How technologies like HDFS, Spark help to handle big data analytics, and how the architecture of these framework works?
So HDFS and Spark. Okay. So what you're describing is possibly a big data landscape. Now, HDFS is a storage layer. It's a storage layer in a Hadoop cluster. So in a distributed landscape, what would happen is, let's look at the distribution of data first. The data would be distributed into different systems. It could be distributed across web servers. It could be in my CRM system. It could be in my ERPs. It could be just some live streaming data that I'm trying to connect to. So the challenge, first step of the challenge would be to bring that data in a format and bring it to a place where we could all store it. Now, since the first step of the pipeline is to do data ingestion and keep it immutable, it is important that we have a large data store, which is where the Hadoop or HDFS can come into picture, which offers key value based storage, and you could typically store the data as you got them with no changes on top of it. Then what you could do is and this is just the storage part of it we are talking, imagine them as disks. Now these disks in a typical data center or in a room could be, imagine you have 5 different pen drives or NAS drives plugged into your machine, and you could just access all of them at the same time. So these disks are again distributed, and what Hadoop will enable you to do is it will save portions of data at a storage level, and it will store multiple copies for failovers and DRs. That's one way of looking at the distributed computing. And then what will happen is, on top of HDFS, we could have services like Spark, we could have a BI layer, which is effectively helping it process it. So now that the data is actively stored and actively coming in also, and we want to process it, we need something like an orchestration manager, which is where Oozie can come in and Zookeeper can come in, which are orchestration frameworks and in Hadoop landscape. So what will happen is Oozie will help you bring in compute job. And again, these computing resources are pulled from a large rack of servers which are distributed, which means that the compute is not sitting on one machine, it's across systems, and the same piece of Hadoop software is running on all those systems. And what Oozie will do is say that, hey, I want to run a Spark. So it will initiate a Spark context, and it will see, or it will serve the need for the requester as to how much memory or RAM it is needed. So if the requirement is to have, let's say, 200 GB, it's obviously not possible to have it in one machine. So what the Oozie is effectively doing is take that 200 GB requirement and distribute it across different machines in the sense of Spark context. And that's where parallelization and distributed computing come in. Now, that's a very high level view of looking at this landscape. So you have distributed data coming in, you have a computing cluster where you have a lot of multiple disks, lot of different computes and Hadoop software running on it. The data came in, you stored it into Hadoop, HDFS, sorry, and Oozie is kind of helping Spark, or Spark is kind of accessing that data in HDFS and it's doing operations. You could also have Hive pretty much do the same. For example, you want to wrap, let's say one of the data stores was a table. So you would probably put a SQL-like language on top of it and you would write query operations. And again, the same thing will happen. Oozie, which is the orchestration manager here, will help Hive access the data in HDFS. It's kind of helping get the resources. And all of this is not happening on one machine, it's happening over multiple machines, which are distributed across the data center. And that is obviously hidden from the implementation. And that's more like infrastructure management perspective. I hope I have answered your question.
Yes, definitely. That would have answered the query. So let's take one last question, Akash.
Sure,
So,
sure.
The person is asking, what are the best languages available for developing end-to-end machine learning systems apart from Python, which are fast and scalable? I think it's a pretty interesting question, which would be
So,
in mind of a lot of people.
I think this is a question I actively keep reading about every few 6 months or every 6 months or so, because the answer to this very rapidly changes. The best answers anybody has ever told me is the language that is known and learned to the team. Scalability is a virtue of the programmer, and security is a virtue of the programmer who's doing it. Yes, there are constraints that languages put, like compiled languages versus interpreted languages, which Python is. However, I was reading a very interesting article around Netflix, and Netflix has a lot of users of Python in their own landscape, in their whole, and in the not, and this is not in the machine learning landscape. This is in the landscape where they are serving videos. So they have a lot of frameworks around which is helping serve the videos and CDNs. So the language war is a pretty popular one, and Python seems to be winning it at this point in time. But Node seems to be equally popular in the world of API development. Angular seems to be very popular in the world of web development. Enterprise systems, large-scale companies are largely dependent on Java or Java-like system like Scala or something. So Java is very popularly used. There's a framework in Java called Spring Boot, very, which is very much used to design microservices. And most of the enterprise systems are built around Java. At least most of my experience has been in Java, in systems working with Java. Then there's Microsoft platforms also. .NET also allows a lot of stuff. And all of these are scalable. Python obviously is there. You have Node, which I already named. And depending on, since this is the machine learning landscape, I think these applications would be more than sufficient. There's also upcoming languages for statistical processing like Julia, which is more like on the emerging side of it for the past few years. And that's a compiled language, nice interpretability with Python and R also. So again, coming back to my original answer, I think it's not the language, it's the programmer. And as a programmer, we should strive to keep learning more languages. Scala is also popular because of pure importance of Spark. And again, Scala is a JVM language, which is Java based. So knowing Java kind of helps in learning Scala also. So yeah, these languages should be good as a starting point.
Thank you, Akash, for answering that. It was indeed a wonderful session. So
All right.
let's continue to our quote.
Yep. Let's just try and do a quick closing remark. And I think Martin Fowler is a very popular enterprise architecture circles, and one of his quotes is, and the way he describes architecture is not by using a diagram or a framework. His understanding is that the collective understanding of the most experienced set of people in the team of the system is what is an architecture. And effectively quoting him, if you're afraid to change something, then it is poorly designed. And this is where the thought of non-functionals play a very strong role, specifically in the new age world of growing data, because as the data grows, so does the technologies that helps ingest and process it and scale it and whatnot. So if we have designed a system which we are always afraid to change, then we have designed it poorly. And the thoughts that go into designing the system, the time that is spent is often reaped at a later point in time, strictly speaking from an enterprise architecture perspective and thinking in terms of a multi-year implementation. So with that, I think I would like to thank you all. Feel free to reach out to Thoucentric for any of the systems around these things. We have implemented these pipelines. We have worked upon demand sensing projects and the problems that we looked over yesterday and we'll be looking at today again. And we are pretty much experienced with all of the different cloud providers and in working with the data that you have in your data center. Extremely experienced with networking and security and adhering to security requirements too. So thank you everyone. Thank you for joining. Over to you, Nick.
Thank you, Akash, for the amazing session.